be studying about what we call as real gases. Now, by real gases, we mean the actual gases that exist. So, let's study a few properties of real gases first. The real gas molecules have a definite volume. Now, if you try to remember, when we were studying ideal gases, we had said in the kinetic theory that the ideal gases are considered to be having a volume which is very negligible as compared to the volume of the container, right? But now we are taking into consideration the volume which is actually occupied by the molecules. The second thing is that the force of attraction between the molecules is not zero. Again, in the kinetic theory, we had discussed that we were considering the force of attraction and repulsion among the molecules to be zero, right? But in this case, we will be taking into consideration those factors. That is, now we are not having any sort of assumptions. But we can say that the real gases behave as ideal ones in conditions of low pressure and high temperature. Now try to imagine this. Say you have a container here and you have a gas inside it, which is a real gas. That is, it has volume and it is having some forces of attractions among the molecules, right? But when the pressure is low, that is, say if this is a piston cylinder kind of a system, the piston is raised up. Now try to imagine the piston is raised up, the volume is huge. So the particles would be very, very far away from each other and therefore would not be able to attract or repel each other as efficiently as they would have done had it been high pressure. And also, similarly, when the temperature is increased, what would happen is that the particle would have higher kinetic energy. We studied this in kinetic theory of gases. And when they have higher kinetic energy, they would try to move farther away from each other, thus reducing the forces of attraction, right? And if the volume is increased to infinity, or if they are moving farther away from each other, we can say that the volume they are actually occupying will be very large as compared to the volume of a particular particle. So that is why at low pressure and high temperature conditions, the real gases also start behaving ideally. Now, to account for this real behavior, we have something which we call as the compressibility factor. And the compressibility factor can be defined as PV real divided by PV ideal. Okay, that is, if we have a sample, the actual pressure into volume which we are obtaining for that sample divided by what would have been the pressure and volume at the given conditions if the gas would have been ideal. That is what we get from the compressibility factor. So we know that for a real gas, we follow the equation PV is equal to nRT, right? So we can write it as PV real divided by nRT, correct? Because temperature is not something which is like real or ideal or something of that sort. And if the number of moles is 1, right, we can write it as V real is the molar volume, right? Because this is what we are actually measuring for that sample. So the molar volume of the sample will be called V real. So we can define Z to be PVM divided by RT, right? Now, if Z is equal to 1, it would imply that PV molar is equal to RT, and if Z is not equal to 1, it would imply that PVM is not equal to RT, right? And if PVM is equal to RT, this implies ideal behavior and this implies real behavior. So now, to define the real gases, we have an equation of state. Like for the ideal gas, we had PV is equal to nRT as our equation. For the real gases, we have another equation which is known as the van der Waals equation. Now, what that equation looks like is P plus an square divided by v square times v minus nb is equal to nRT. Now let's try to understand the significance of all these terms. Here, the first term, which is P plus A n square divided by V square, is basically equal to P ideal. The P we put in here in the equation is real. The V is also real. Okay. And similarly, we can say that V minus NB is equal to V ideal. So basically, we can say that A, n square by V square, and NB, both of these are correction terms. The correction terms in the real pressure and volume, so that the equation can look something like the ideal gas equation. So let's see what these terms are. If we talk about A n square divided by V square, this is basically, as we talked, the correction term in the pressure to be considered. So why does this term come up? Let's talk about that. Let's say that we are having a container which has gas in it. Here is the container. Had the gas been ideal, right, it would have struck the container, and the pressure due to that would have caused the P ideal. However, now the gas is real, right? Now, since the gas is real, these particles are attracting this molecule towards themselves. So, whichever molecule is trying to go towards the boundary is being attracted by other molecules. Now, try to think of it in this way. Let's say there is a wall and you are standing here trying to push the wall, right? You are here trying to push the wall. But if we take a rope and start pulling you in the opposite direction, would that push be as efficient as it would have been had this rope not been there? No, right? The push would be inefficient. So, similar case for these molecules. The P real which they are exerting should be less efficient than the P ideal, because the P real is being diminished because of these forces of attraction by the other molecules. So, therefore, if we look at this expression, we can very clearly see that P ideal is greater than P real, right? And this is the correction term to account for these forces of attraction. Next, if we look at this second term, NB, this is the correction term in the volume, in the real volume, right? So if we look at this diagram, this concludes that the effective volume for a single molecule would be half of the volume that is occupying, and the volume that it would be occupying will be 2r. This is basically the distance, right? The effective distance. And multiplying it with the Avogadro's number, we would get it for 1 mole. And so B is basically defined as 4 times the volume occupied by 1 mole of molecules. That is 4 times n naught times 4 by 3 pi r cube. And it is accounting for the actual volume of the molecules. So in the ideal scenario, we were not considering the actual volume, right? And in the real scenario, since we are considering those volumes, therefore the real volume should actually be greater than the ideal volume, as can be clearly seen here. Now let's talk about the compressibility factor for the real gases. How had we defined the compressibility factor? It was PV real divided by PV ideal, right? So let's use the van der Waals equation to find what the compressibility factor for such a gas would be. So the van der Waals equation is P plus A divided by V square. Here we are taking it in a per molar sense, right? So N is 1 into V minus B is equal to RT. Now let's just open this up. PV minus PB plus A by V minus AB divided by V square is equal to RT. Now A and B are actually small quantities. Okay, they're not as large as the extensive pressure or volume can go. So this term is generally ignored because it has a product of two very small quantities and becomes negligible as compared to the other terms in this equation. Next, what we do is we write it in this form. PV is equal to RT plus PB minus A divided by V. Now we know that PV real by PV ideal can also be written as PV divided by RT, right? So let's just do that, dividing by RT on both the sides. When we divide by RT on both the sides, what we get on the left hand side is PV divided by RT. Let's call it Z straight away. And on the right hand side, we have RT divided by RT, which is 1, plus PB divided by RT minus A divided by VRT. Correct? So this is basically our expression for Z. Now let's talk about a few scenarios. The first one is at low pressure. So when the pressure is small, what would happen when the pressure is small? In this Z term, this first term would get ignored when P is small. And due to the ignorance of the first term, the final expression would become 1 minus A divided by VRT. And this comes out to be equal to your Z, that is at low pressure. And if we observe, this Z is less than 1. So we can also conclude that at low pressure, the gas shows a negative deviation from ideal behavior. And now when we talk about high pressure, we can say that at high pressure, the term containing V would get ignored. And when that happens, what we will be left with is Z is equal to 1 plus PB divided by RT. That is, Z is greater than 1. And so we can say that at high pressure, the gas shows positive deviation. Now let's talk a little about A and B. We know that A and B are small quantities which define some properties of a real gas. A is used in the correction term for pressure and B is being used in the correction term for volume. But then let's talk about their units. If we talk about A, we can say that in the term we had P plus AN square divided by V square. Right, this was in one bracket. So by dimensional analysis, we can say that AN square divided by V square should have the units of pressure. So let's write it as A will be equal to pressure times volume square divided by N square. So this will be Newton per meter square. Pressure is force upon area. Volume will be meter cube square and the denominator would be mole square, right? Or volume we can also take in liter square. Why? Because we generally take R in units of liter, right? So let's take volume in liters. And so we would have Newton liter square per meter square mole square. These are the units of A. And if we talk about B, for B we have the term V minus NB. So therefore NB should have the units of volume. That is, B should be volume divided by number of moles. That is liter mole inverse, right? So the units of A and B are respectively these.